Okay, just want to get rolling for our second hour here. In race sake here, I passed back the test. For those of the other locations, you should have received an email in your WITC account with your test in it. If you tried to open it at home, you might not be able to see the ink to show you my grading. If you open it on a WITC computer, you should be able to see the inking and see which ones you got wrong and stuff like that. If you can't, let me know and I can send you which problems, tell you which problem numbers you had wrong. If you open it at home, a lot of times you'll just see a copy of the test with nothing marked on it. Now that you have the tests back, you're not necessarily done with them. I do allow you to redo all the problems you got wrong and turn them back in, and I will give you up to half your points back. So if you redo every one of them and turn them back in, you can get half your points. So let's say you had a 78, that'll turn that into an 89 with half your points back. Or a 92 can become a 96. You are allowed to work together if you want to correct them. You don't have to go off on your own. If you can't figure out how to do one, ask me. I'd be more than happy to walk you through one of the problems so you know how to do it. So make sure you do that. Those points could count up later. Okay, anyway, so for now, let's get going with our next step. So we've talked about solving some of these more complex equations with the fractions and stuff in them. The next step is to look at an equation that doesn't have any numbers in it. For example, we've looked at 3x plus 7 equals 25. And we solved that. We subtracted the 7 and then we divided by 3. But what if that equation were ax plus b equals c? How would we solve that? First thing we'd have to know is we'd have to know what we're solving it for. Now, since there's an x in here, we just assume we're going to solve for x. But we really should look to make sure we're solving it for x. So now we're going to solve this one exactly like we would solve this one. Here we would subtract 7. Down here we're going to subtract b, make it go away. Here goes ax. It's a little bit different though, is c minus b is just c minus b. You can't combine them. Next, x has been multiplied by a. We're going to divide by a to get rid of it. X equals c minus b divided by a is just c minus b over a. And that's it. All done. Now, most of our formulas are not quite that difficult. For example, we might have area is equal to length times width. You might be asked to solve that for the width. So doing that, first we find the variable that it is we're solving for. Here it's w. And just like with any equation, any other equation, we find the equal sign. The w is over here. And we ask ourselves, what's keeping w from being by itself? In this case, it's the L. The L is multiplied, so to get rid of it, we are going to divide. So we divide by L to make it go away. A divided by L is just A divided by L, or A over L. So A over L equals W, or W equals A over L. We might have something like R equals P over 3 times A plus B. You might be asked to solve for A. Here's A, which means I got to get rid of everything else. If I look at what has been done to A here, first of all, we see the parentheses. If there were numbers here, I would take this and I would distribute it. But there aren't numbers here. I could still distribute it, but it's going to get really ugly. But we can look at it this way. If I use the parentheses, A has had B added to it, then it's been multiplied by P over 3. So to reverse that, I'm going to divide by P over 3. That goes away. I'm left with A plus B. Now, R divided by P over 3 is a little bit tricky. R divided by P over 3, I'm going to make this R over 1 times 3 over P. R times 3 is 3R. 1 times P is 1P, or just P. So this is now 3R over P. And then I'm solving for A, so I got to get rid of everything but A. Get rid of the B, it's added, so I'm going to subtract B. So over there, all I have left is A. Over here, 3R over P minus B is 3R over P minus B. What do you think? Headache waiting to happen?
Oh, it's already there.
It's already there? Sorry. I guess I deserved that answer. On a slightly simpler note, you might have 16x plus 2y equals 34. You might be asked to solve for y. This one's a little bit tricky because we're so used to solving for x. Now we're solving for y here. Y has been multiplied by 2, and 16x has been added to it. To solve, I'm going to subtract 16x. So I'm left with 2y. What's 34 minus 16x? Trick question. It's 34 minus 16x. This is where it gets a little trickier. Y has been multiplied by 2, so we're going to divide by 2. Y equals, well, over here we can divide by 2. Each number gets divided by 2. What's 34 divided by 2? 17. Negative 16x divided by 2 is a negative 8x. What do you think? A little bit better? Throwing some numbers in there helps. We can run into something like this. In our next unit, we're going to run into a concentration adjustment formula. It's going to look something like this. Now here we've got V's and C's, but we actually have 4 different variables here. The V and the 1 here actually combine to make one variable. That's saying the first volume, V1. The V and the 2 here combine to make a second variable. That's saying the second volume, or V2. So V1 and V2 are different. V1 is the volume of the first solution. V2 is the volume of the second solution. Just like C1 and C2 are going to be different. C1 is the volume or the concentration of the first solution. C2 is the concentration of the second solution. If I ask to solve this for V1. Well, here's V1. What do I have to get rid of? C1. It's multiplying V1, so I get rid of it by dividing by C1. So I'm left with just V1 over here. V2 times C2 divided by C1 is just V2 times C2 over C1. There's absolutely nothing I can combine there. Another thing we can do with our variables and formulas is we can look at evaluating. If we're asked to evaluate something like D equals 5m minus G, evaluate for D when m equals 3 and G equals 7. What that's telling us to do is find the value for D when m is 3 and G is 7. 5m is 5 times 3. I replaced the m with 3. 5m is really 5 times m, so it becomes 5 times 3. Minus g is 7. So I put 7 in where the g is. 5 times 3 is 15, minus 7 equals 8. D equals 8. What do you think? Not as bad? That's better? We're going to use these a lot in our next unit when we get to, or actually we're going to use these a lot next week when we do some measurement conversions to convert Celsius to Fahrenheit or Fahrenheit to Celsius. Your Fahrenheit temperature is equal to, it's 9/5. Your Celsius temperature plus 32. So evaluate for F when C equals 35. Is 35 degrees Celsius a hot day, cool day? 35 sounds pretty cool, doesn't it? So I'll evaluate for F. This will be 9/5 times 35 plus 32. I'll make this 35 over 1 so I can multiply them. Cross cancel the 5 and 35, give me 1 and 7. 9 times 7 is 63. 1 times 1 is 1, so it's just 63. So F equals 63 plus 32, which is 95 degrees. F is 95. The formula for BMI is a person's weight in pounds divided by their height in inches, height squared, times 703. I'm not going to ask for volunteers. I've learned a little bit through the years. Let's say we have someone who has a weight of 250 pounds and a height of 73 inches. Their BMI is going to be 250 over 73 squared times 703. So we have the fraction bar here means we have to do everything on top first. Well, there's nothing to do on top. Then we have to do everything on bottom. On bottom, we have 73 squared. 5329 times 703. Now, we're going to divide. 250 divided by 5329 is 0.0469 times 703. So I'm just going to leave that in the calculator and multiply by 703. That keeps me from getting the big round off here. So 32.98. So that particular person would have a BMI of 32.98. Anybody know what normal range is?
That would be high.
That would be high, I'm guessing. Yeah.
Yeah.
Under 20, I think, is normal. Is that what it's supposed to be?
It depends on, I work at Health and Wellness Center for like you, and just depends on your male, female, and age.
Oh.
Guys should probably be in 20%. Women, that's a little high.
Still a little high?
Women are a little higher, but I can't remember.
Okay.
Yeah. Probably not past 29%.
Okay. I've never known what those are supposed to be. I try not to pay attention to some of that stuff. Next topic. Let's move away from the equations a little bit and talk about something a little different. What we're going to talk about next is probably the most powerful tool in math. And it's actually not too bad to work with. It's one of the simpler ones, but it can be applied to so many different things. How about the concept of a ratio? A ratio is nothing more than a comparison between two numbers. For example, I could do a female to male ratio. I'm looking around the room. We have what? 1, 2, 3, 4, 5, 6. Looks like we have 6 female students to 3 male students. I could write it just like I did there as like a fraction, 6 over 3. I could write it with a colon, 6 to 3, like that. Or I could even write it with the word 2 in it, 6 to 3. And there are some other less common notations out there we could use. This one's pretty common. This one is very common when we're going to do any calculations with it. Using that fraction notation allows us to do a lot of stuff with it that we would do with a fraction. For example, both 6 and 3 can be divided by 3. 6 divided by 3 is 2. 3 divided by 3 is 1, giving me a 2 to 1 ratio. I could reduce each of these then to 2 to 1 as well if I wanted to. I can still reduce it in these forms. It's just more familiar to us to reduce it as a fraction. Now, one big difference between the ratios and a fraction is if this were really a fraction, I would reduce it to just 2. It'd be a whole number. But a ratio is a comparison between two numbers. So I have to keep two numbers. So it would stay as 2 to 1. I might do a ratio of, the tables in this classroom here. The width to length. The width is 18 inches. The length, 6 feet, would be 72 inches. So if I reduce that, first of all, the inches divide out, and both of those can actually be divided by 18 to reduce to a 1 in 4 ratio. Now, there's no units in that ratio. You notice the inches divided out. What that means is on these tables, for every 1 unit of width, there is 4 units of length. Doesn't matter if that's 1 inch of width. For every 1 inch of width, there'll be 4 inches of length. Or 1 foot of width, there'll be 4 feet of length. Or 1 centimeter of width, there'll be 4 centimeters of length. Whatever it is, it's saying that ratio, 1 to 4. Doesn't matter what units are used. You'll notice in both of the examples I just did, the two numbers had the same name or the same label. This one compared inches to inches. This one compared students to students. And that is a characteristic of a ratio, is it must compare two things with the same name or the same label. I could not do 2 feet over 18 inches. That is not a ratio. Now, fortunately, I could change it. 2 feet is 24 inches over 18 inches. Now it's a ratio, and it can be reduced. Inches can be divided out. 24 and 18 can both be divided by 6 to give me a 4 to 3 ratio. Another difference between the ratios and fractions, if this were a fraction, we'd make that 1 1/3. Ratios never become mixed numbers. They're always a comparison between two numbers. So we've said that ratios compare two things with the same name. What happens if we compare two things with different names? Let's say that we want to go on a little bit of a road trip. And let's say that you are going to travel 365 miles and it takes you 7 hours. Here we're comparing miles to hours. There is no way to convert miles into hours or hours into miles. This is not a ratio. It is what we refer to as a rate. So the first big difference between a ratio and a rate is a rate compares two things with different labels or different names. The second big difference is a ratio we tend to just reduce down like this, 4 to 3 as far as we can, but we don't get into fractions or decimals or anything like that. Rates are almost always reduced to what we call a unit rate. What that means is the bottom number gets reduced to 1, or we divide by that bottom number. So we divide by 7 here to get 1 hour. We divide by 7 up here to get 52.142857,143 approximately miles. Don't worry, it's not contagious.
I wish it was.
52 point whatever miles per 1 hour. In fact, once it's in a unit rate, we often get rid of that appearance of the fraction, and we'd write it as, if I round this to 2 decimal places, 52.14 miles per hour. The fraction is hidden in the units. I mean, we even go one step further sometimes and do 52.14 mph. mph, of course, stands for miles per hour, which is fine. We just have to remember, whenever we see this, it means this, because that's the form we need it in to calculate. If you're told that your car gets 26 mpg, what's mpg stand for? Miles per gallon. We need to see that and think this. 26 miles per 1 gallon. Because this is the form we need it in to do our calculations. Next unit, when we do dosage calculations, we're going to just do a ton of those. So we have all sorts of rates out there as well. We saw miles per gallon, miles per hour. In the medical field, if you're doing an IV, you might have units per hour. Let's say you're going to deliver to the patient 4,000 units of medication in 8 hours. The rate, 4,000 units over 8 hours. If you divide that out by 8, 500 units per hour. Other rates you'll see. GTT is an abbreviation used for drops. So you might have an IV that is set at 300 drops in 12 minutes. That's going to be 300 GTT over 12 minutes. That'll divide out. 300 divided by 12 is 25 drops per minute. Or on a drop factor. A drop factor for medications is based on the viscosity or the thickness of the liquid. Really thick liquids might be as low as 8 or 10 drops per milliliter. The really thinner ones can be 20 to 25. I think most of what you use in medical is between 12 and 20. Drop factor might say 12 drops per milliliter. That's saying every milliliter of liquid has 12 drops in it. And there are, of course, other ones that you're used to. $8 per hour, that's a rate, that's wages, dollars per hour. It's written a little bit different, but it's still out there. And rates are all around us. Ratios are all around us as well. We look at comparing students to female to male, width to length. We run into all sorts of ratios. If you go to get a loan, they'll look at a debt to income ratio. What they're looking at is your monthly loan or monthly required payments. That'd be like a mortgage or a rent expense, car payment, whatever. Let's say you have $1,200 a month in debt payments and your income is $3,000 a month. Each of those can be reduced by 300, which gives us, I could reduce by 600. 4 to 10, I can divide by 2 again. Gives me a 2 to 5 debt to income ratio. They prefer your debt to income ratio for most loans to be below 1 to 3. So 1/3 of your income per period is required debt payments. You might have a student to teacher ratio. If you have 72 students, 3 teachers, That reduces to 72 divided by 3 is 24 students per teacher. And there's ratios all around us. You might be looking at a medication that you're going to constitute. It might say you're going to mix it 300 milliliters of saline to 120 milliliters of lidocaine. This is a ratio of 300 milliliters to 120. Notice again, they have the same unit, milliliters. Both of those can be divided by 60, giving us a 5:2 ratio of saline to lidocaine. So with these ratios, if we know what the ratio has to be, we can use it then to figure out the second part to one of those numbers. We mentioned a debt to income ratio. They prefer you to have a 1:3 debt to income ratio or below. So let's say you have a monthly income of $4,200. If I want to figure out then what is the maximum amount you should have in debt payments, I'm going to set it up as a proportion. This ratio, 1:3, has to equal this ratio with the $4,200 as your income. The 3 represents the income, the $4,200 also is your income. Those numbers have to match up like that in the proportion, just like we did with percents a couple weeks ago. So now to find that missing number, we can cross multiply. 1 times 4,200 is 4,200. We're going to divide by the 3, which is going to give us 1,400. So if you have a monthly income of $4,200, you should not have debt payments of more than $1,400. Let's see. If you have a 2:5 ratio, we use a generic term for medication in this class. We just call it Serum. That's your concentrated medication. For sterile water or saline, we use the abbreviation NS. It can stand for neutral solution or normal saline, either one. So if we have a 2:5 ratio of medication to our sterile water, we need to know if the patient requires 400 milligrams of that medication, how much water do we need to mix with it? Well, we'll cross multiply. 5 times 400 is 2,000. Then we're going to divide by 2. Gives us 1,000. Units here is milligrams. Units here has to be milligrams because the units have to go away. This is a ratio, so the units have to be the same top and bottom. So it requires 1,000 milligrams of water. We can also use a ratio with our rates. If you have a rate of, well, let's just say we know that the patient is receiving 1,200 milliliters of IV over a 2-hour period. And we want to know, let's say we're going to be leaving, we want to set it up for the night so it runs. We want it to run for 8 hours. How much do we need in there? The 8 hours have to go on bottom because they need to match up with the hours in the other rate. On top here, then it'll be milliliters because it's milliliters over here. And again, we can cross multiply and divide. 1,200 times 8 hours is 9,600. That'd be milliliters hours, which is a nonsense unit. Dividing by 2, it gives 4,800. So 4,800 milliliters in that IV would make sure it got through 8 hours. If we have 700 micrograms of medication, and we want to convert that to milligrams, we know that 1,000 micrograms in 1 milligram. So we can cross multiply and divide. 700 times 1 is 700. Divided by 1,000 is 0.7. So 700 micrograms is 0.7 milligrams. We might have a medication that lists 12 milligrams per kilogram. So if we want to know how much medication for a 30 kilogram patient. So 12 milligrams per kilogram, remember, is 12 milligrams per 1 kilogram. Where's the 30 going to go? Top or bottom? That's kilograms. Has to go with the other kilograms. 30. 12 milligrams times 30 kilograms. 12 times 30 is 360. Divided by 1 is 360. What's the units here? Has to be milligrams. 360 milligrams. Let's say a medication is to be mixed 3 parts in 20. 3 parts in 20 parts. That's a ratio of 3 in 20. I want to know, there's going to be 3 parts serum and 20 parts of sterile water, initial solution. How much sterile water, NS, for 60 milliliters of serum, of our medication? Where's the 60 going to go? $60 milliliters of serum. This is 3 parts of serum and 20 parts. So the 3 represents the serum. So 60 milliliters also represents the serum, so it goes on top. Cross multiply 20 times 60. 1,200 divided by 3 is 400. Units will be milliliters. Since this is a ratio, if it has no units here, that makes it a ratio. That means the units here have to be the same on top and bottom. Here it was a rate because it had units here, different units here. So when it's a rate, the units here and here have to be the same. Units here and here have to be the same. Like I said, that is probably the most powerful tool in mathematics, is those rates and ratios and proportions. Because 90% of what we do in math can be set up as a proportion and solved that way. Right up into our trigonometry can be set up as proportions. Okay, well, another thing we want to look at here, just kind of a build up so that we can deal with the next topic. What does that mean? 8 to the 3rd power. And if we didn't have a calculator, how would we calculate it? 8 times 8 times 8, or 512. Before we do anything else, does everybody know how to do that on your calculator? On your calculator, you'll have one of 2 keys. You'll have a caret key that looks like that, and a little up arrow. Or you have a phone calculator?
Yeah.
You might have an X to the Y key like that.
I don't have any of that.
You don't have any? Put your finger on the screen and slide it to the side once. Or the other way. Oh. Is there a mode key on the bottom of it somewhere? Sometimes you can hit mode and turn on scientific mode or something like that. Turn your phone sideways and see what happens. Does that make more keys?
It's not
You have to have it on your calculator though.
You have to what?
Have the calculator turned on?
Yeah, but it won't. My phone's having issues and won't let me flip it.
Won't let you flip it? It wasn't automatically change?
Yeah.
The gyroscope's bad in it or something? A lot of times if you're using a phone calculator, either you turn it sideways and it'll come to scientific mode, or you take your finger and swipe it to the side and it'll have the other commands off to the side of the screen.
Yeah, my phone's not
Alright.
working properly.
But anyways, to use that, you would take 8, you'd press that key, whichever one you have, and then the 3, and it should spit out 512.
So they're both the same thing.
Yeah, both those keys work exactly the same way. If you want to test it, let's do 5 to the 6th power. 15,625. Okay. Well, we're really not, the purpose today really isn't to do a lot of calculating like that. It's to start looking at what happens if we have variables with powers. Of course, x to the 3rd power, just like 8 to the 3rd power meant 3/8 multiplied together, or 8 times 8 times 8. X to the 3rd power means 3 x's multiplied together, or x times x times x. So if that's the case, what is x to the 3rd times x to the 5th going to give us? Well, you would think that 3 times 5 would be 15. That would make sense, but let's look at it. X to the 3rd is 3 x's multiplied together. X to the 5th is 5 x's multiplied together. If I multiply them all together, there's 8 of them. That's x to the 8th. When we're multiplying variables with exponents, it looks like we're adding the powers. And that's the shortcut. We're just going to add 3 plus 5 is 8. But we are actually multiplying. It's just, it looks like addition. So if I have y to the 9th times y to the 12th, I get y to the 21. 9 plus 12 is 21. What if I have x to the 5th divided by x squared? Plug in 5 x's multiplied together. X squared is 2 x's multiplied together. Cancel out 1, cancel out 2. What am I left with? X to the 3rd. Again, I am dividing, but it looks like we're subtracting. 5 minus 2 is 3. So if I have y to the 11th divided by y to the 7th, I get y to the 11 minus 7 is 4. P to the 9th divided by p to the 3rd gives me p to the 6th. 9 minus 3 is 6. X squared to the 4th power. That's x squared times x squared times x squared times x squared. 4th power means there's 4 of them. Well, x squared, of course, is just x times x, right? How many x's are now being multiplied together? 8 of them. I'm not about to write out all these x's, but how many of them would there be? There's x to the 5th 7 times, 35. When we're taking a power to another power, it looks like we're multiplying. 5 times 7 is 35. So if I have y to the 8th to the power of 3, that's y to the 8 times 3 is 24. Very good. To define x to the 0, let's take a look at another number like, oh, I don't know, 8 to the power of 0. If you punch that in your calculator, it'll give you an answer of 1. Technically, according to the definition of a power, we really can't do anything to the power of 0. How do you multiply something by itself 0 times? Well, like we mentioned this with our negatives or integers. There are a lot of times in math where we run into a place where the definition doesn't work. Technically, we can't do that. So what we do is we look for a pattern. 8 to the 3rd power is 512. 8 to the 2nd power is 8 times 8, or 64. 8 to the 1st power is 8. So the pattern here, when we start out with a base of 8 in our exponent, whenever we reduce the power by 1, The answer is divided by 8. Reduce the power by 1, that's divided by 8. So if we kept going, 8 to the power of 0, we reduce the power by 1. What's 8 divided by 8? 1. 8 to the power of 0 is 1. In fact, anything to the power of 0 is 1. X to the power of 0 is 1. 752 to the power of 0 is 1. I used to do this one on quizzes until I realized it was no longer safe for me to go in the parking lot. That is 1. Doesn't matter what all this is, it's the power of 0. It's 1. Anything to the power of 0 is 1. Well, let's keep going with this pattern here. What if I decrease the power by 1 more? 8 to the power of negative 1. The pattern has to continue. Now again, it makes no sense to multiply 8 by itself negative 1 times. But if I continue the pattern, I divide by 8, this is 1/8. 8 to the negative 2, dividing by 8 again, this is 1/64. If I went one more, 8 to the negative 3, I do 1 over 512. We notice a correlation between the negative powers and the positive powers. 8 to the power of negative 2 is just 1 over 8 to the positive 2. 8 to the negative 3, 8 to the third was 512. 8 to the negative 3 is 1 over 512. 1 over 8 to the third. So x to the negative 5th power is defined to be 1 over x to the positive 5th power. The reason I'm showing you this is to go back to our place values that we looked at in the first week. Our place values had definite values to them, numerical values. We have our number system is defined to be a decimal number system, or what we call a base 10 number system. What that is talking about are these exponents that we were looking at up here. This is 10 to the power of 0 is 1. 10 to the power of 1 is 10. That's the tens place. 10 to the power of 2 is 100. That's our 100s place. 10 to the power of 3 is 1,000. Thousands place. 10 to the power of 4 is 10,000. 10,000s place. And so on. 10 to the power of 5 is 100,000. 10 to the 6th is a million. Going this way, 10 to the negative 1 is 1/10. 10 to the negative 2 is 1/100th. Our place values are nothing more than powers of 10. If you're in computer science and you're looking at, computers tend to think in either on or off. So they think in base 2. There's only 2 possibilities, 0 or 1. So they deal with binary numbers. Same concept, instead of 10, it's 2 for each of the place values. Sometimes they group them into octal numbers, so instead of 10, it'd be 8 for each of those place values. You guys aren't in computer science, so you don't have to worry about it. But where it comes in for us is this. If I have like 8,200,000, sometimes to abbreviate that, we would write it as 8.2 million. Well, the 8 is in, the reason they say is 8 is in the millions place. So we leave that as, we say that as millions and leave the rest after a decimal point. Well, another way to say millions is 10 to the 6th. This is our scientific notation. So let's say we have, I'm going to write it up above here, 750,000. To put that in scientific notation, we take the first digit, which is the 7, 7.5. Everything after that first digit goes after the decimal point. What place value is that 7 in? It's into the 10 to the 5th place. That's where scientific notation comes from. Now, we don't want to draw out the place values and put it on there to put stuff in scientific notation. We were taught a shortcut, and what it was this. Decimal point's right here. But for scientific notation, I have to have it so there's only one digit in front of the decimal point. One non-zero digit. How many places do I have to move the decimal point? 1, 2, 3, 4, 5 places. 10 to the 5th. Makes sense? So if I have 98 million and I want to convert it into scientific notation, of course, the decimal point is going to go here. It's going to be 9.8. How many places do I have to move the decimal point? 1, 2, 3, 4, 5, 6, 7. 10 to 7. Here, I need to move the decimal point there, so it's going to be 5.3. But these are the negative place values. This is negative 1, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. Same thing works. 1, 2, 3 places. That's where the negative 3 comes from. I just have to remember this is a small number, so it's in the negative place values. If I wanted to convert the other direction, if I have 3.17 times 10 to the negative 5th, that power of 10 tells me I'm going to have to move my decimal point 5 places. The fact that it is negative tells me that this is a small number. So I have 3.17. My decimal point has to move to make it smaller. 1 spot. There's nothing left. Just have to add a 0. 2 spots. 3 spots. 4 spots. 5 spots. There's where my decimal point is. 0.0000317. Or I might have 7.02 times 10 to the 4th. Again, my decimal point's got to move 4 spots. It's a positive power, so this number is a big number. So I have to move the decimal point 4 spots to make it bigger. 1, 2, add a 0, 3, add another 0, 4. 70,200 is what that represents. Any questions? We're going to lose the network in just a minute, so for homework, I do want you to keep working on the mixture problems on page 53 through 54. On page 60 through 61, solving the fractional equations. And page 67 through 68, evaluating expressions. There goes the network, so I'll put it in the recording. Page 73, we're dealing with the ratios and proportions. Page 78 is a little bit of a review of percents. Page 84 and page 87 talks about the powers and the scientific notation. On page 84, only do 1 through 31, the odds. And on page 87, only do 1 through 39, the odds. With that, I guess have a great week.